Now let's try to understand what exactly this conv1 layer is. Okay, so input we know it's 227 by 3. The first convolution layer has 96 different kernels, right? And each of these kernels has a shape of 11 cross 11. So that's indicated here. And these filters will be applied at a stride of 4. So by now you should understand like each of these terms. 96 should be fine, that many filters. This is just the shape of the filter. And stride, you know, like when you move your filter, how many pixels you will skip in between. Now, with all these parameters known, you can usually you can easily use the formula which I showed you in the last lecture to compute what will be the shape of the output activation map. Okay, you can just apply like that formula. You have all these variables here. The other point here to note is it's just saying it's 11 cross 11 filter, but as you know that your filters are like 3-dimensional. So the third dimension here will be 3, so which is not stated here, but in fact the filters will be 11 cross 11 cross 3. Okay, the third part is implicit. Now, if you use like the formula which we already know, you can just put it there, and that will give you number 55, and that's why you have like 55 cross 55 resolution of the output activation map. And the third number, which is like the depth of the activation map, which is 96. This 96, as you know, is coming from the number of kernels we have. So we have 96 different kernels, which means we will get 96 of these activation maps. Okay, so that was the first convolution layer. And similarly, I mean, you can go through like the whole architecture here, and you will be able to understand like how we are going from 224 to 55 or 27 and then to 13 cross 13 to 256. We just need these variables and the equation. Okay, so now the question is, if you're using that many parameters, then how many total parameters or trainable parameters are present in this first convolution layer? And again, which is easy for you, you know that you have 96 different kernels. Each kernel has a shape of 11 cross 11, and you also have a cross 3. So which means that you have that many values to learn in this layer, which represents the number of parameters. You can just multiply those. So it becomes 11 cross 11 cross 3 cross 96, which turns out to be 35,000. Okay, so in your first layer, you have 35,000 parameters. Now let's move on to the next layer, which is max pooling layer here. Okay, so after conv1, you were getting 55 cross 96. After that, we have this max pooling layer where the filter size was 3 cross 3, and this was applied at a stride of 2. And again, if you apply the same formula here, that will give you the size of the output activation map, which is 27. All right, so that's how you get 27 cross 27. And the depth of the output will be 96. So in fact, the output of the max pooling is not shown here. Okay, so the output will be 27 cross 27 and then 96. And then after that, you will apply the second convolution layer, which is giving you this 27 cross 27 cross 256, which means in the second convolution layer, you might have 256 different kernels. Okay, so I think we had like a pop quiz last time, how many parameters we will have in this layer. So max pooling will have 0 parameters because we are not learning anything there, right? We know the function which can be used to perform that, excuse me, that operation. Okay, so after the max pooling, we have a normalization layer. And again, as I said, we just try to limit the values between certain range. So the size of the activation map should not change. It's just the values in that activation map will change. Okay, so the shape will remain the same. Now that was like the first 3 layers, but at the end, like this is like the full configuration of AlexNet. It's giving you the details of like for every layer, how many kernels you have, what was the size of the kernel, in this case 5 cross 5, and it's also giving you like the parameters, what's the stride, what's the padding. Okay, so all these numbers shown here, these numbers are not parameters of your network. These numbers are hyperparameter of your numbers. So there's a distinction between parameter and hyperparameter. Okay, Parameter is something which is learned when you train your network. Okay, so those values in those activation maps. But the numbers which define the architecture or which defines like the training of your architecture, those numbers are called hyperparameters. So parameters, you have no control, they will be learned during the training, but hyperparameters are something which will have to set even before starting the training. Okay, so all these are hyperparameters. Like how many kernels you have to use, you have to make a judgment. What should be the size of the kernel? Again, you have to make some judgment. Again, all this thing, like what should be the stride and everything. So the architectural details of the network, these are called hyperparameters. Okay. So once you have these hyperparameters, then you know what your network is. I mean, with all these details, you don't need anything else. So irrespective of which deep learning framework you use, so deep learning framework is something like where you can train your models. Okay, so it's some kind of backbone framework which is provided. So irrespective of which framework you're going to use, your network will not change if you use like these set of parameters. Okay, you can use PyTorch, you can use maybe TensorFlow. The architecture is fixed. So now let's quickly look at like the number of parameters we have in each of these layers. The first layer we already saw that we had roughly 35,000 parameters. Similarly for Con2, you can do the computation here. You just multiply 256 by 5 and then by 5. And then you know that the depth of the filters in the second con layer will be 96, right? Because the output of the first layer gives you like a depth of 96. So the third dimension is implicit. So if you multiply all those numbers, it will give you around 614K. Similarly, you can keep computing these. So you have these numbers here. Okay. So now one interesting thing to note here is these are the number of parameters which you have in the convolution layer. But as soon as you move to the fully connected layers, so you can see like you have like 4096 neurons here and this one and 1000 in the last one. You can see the number of parameters. It's like a lot. I mean, it's too high if you compare that with the convolution layers. And again, the reason is in the convolution part, we are actually sharing the weights, right, or the kernels across space. But that's not happening when we have these fully connected layers. For each connection between neuron in your input layer to the neuron in the second layer, the next layer, you have a different weight. So that weight is not being shared, and that's causing like a huge jump in the number of parameters which are required to train in these fully connected layers. Right? So you can see like majority of the weights are actually coming from these fully connected layers.